In the last video clip, we just saw an example of an isomorphism, meaning that we were able to take an abstract vector space that's not necessarily Rn, and we could translate it, translate each of the basis vectors into one of the standard basis vectors in Rn. And that's our tool. That is what we need in order to represent now any linear transformation as a matrix in Rm by n. And here's the path. Up here on this diagram is the transformation T that goes from V to W. And this is the abstract realm. And then coming down this way, we have Rn and Rm, which is more of the concrete realm. So notice that to get from V to W using the transformation T is the direct route. And for those of us who don't like to work in the abstract realm, like computers, we need to take a detour around to get from V to W. So to represent T non-abstractly, we take the detour where we first come down this way from V to Rn, and then from Rn to Rm, and this is a matrix. The S is what we call the matrix representation of T, and then the final leg of our journey would have to go from Rm to W. So I've written some extra things on here, and I want to explain this A inverse and this B, and the easier one to start with is B. Once we are from Rm to W, this is what we did in the last clip, and that is where we represent each of the identity matrix columns, each of the standard basis in Rm. This is how we represent it in terms of, or translate those columns into basis vectors in W. And so going on the other side of this arrow, notice this arrow goes in the opposite direction. This is going from V to Rn, and so this is just the reverse process, which is why that is called A inverse. So in order to go from V to W, we first take A inverse, and then do S, and then do B. So it's isomorphism, matrix multiplication, and the other isomorphism. Notice also these are both basically representing identity. This is not changing any of our vectors as we go vertically on here. It's isomorphism means we're keeping things essentially the same. We're just breaking them from the abstract to the concrete, or the other way around, from the concrete to the abstract. So now in writing these equations down here, the representation of T in terms of S, but also the representation of S in terms of T. We have to remember that we are reading from right to left in mathematics here. And that is, if we start with V, we take a vector in V, and the first thing we do to it is we're multiplying by A inverse. And so if we have a TV, we have to put A inverse V first. And then on top of that, we're stacking the S, and then the last thing we stack onto there is B. And if we were to solve this matrix equation to get rid of B on the left, we would put B inverse on the left, and to get rid of A inverse on the right, we'd have to put A on the right. But that's also like saying if we want to find S, we're going from Rn to Rm, and representing something abstract, we would first have to transform ourselves into the abstract realm, which is going against the arrow, would not be A inverse anymore, but it would be A, representing the basis vectors identity in terms of the basis vectors V. So that's the inverse of A inverse. That's just the normal representation process, A. And then we can do the transformation T, and then we come back this way, and notice going against the arrow again means we switch from B to B inverse down there. So now the examples that we do, we actually use this one. This is the theoretical result. This is the applicable result. Because usually We know how to do the abstract transformation. It's representing it, coming up with S. That is our problem. Or the problem that we're looking to solve. Like, it's not our problem, we're trying to solve the problem. And so this is the one that we use most often, and that is, again, we first represent back to the polynomial space in the example, or to the abstract vector space, where we can perform the transformation T, and then it's represented back in terms of columns. That's the 3-step procedure that we will do in that next example.